Hi everyone and welcome. In this video, we're going to take a look at L'Hopital's rule in detail and see how it can be used to evaluate limits of the form 0 over 0 or infinity over infinity. These are something called indeterminate forms, and there's other types of indeterminate forms that we're going to take a look at in future lessons. To get started, let's suppose that you're trying to evaluate a limit of this form. The limit as x approaches c of f of x divided by g of x, where you notice that both the numerator and denominator are approaching 0 as the inputs approach this limiting point. Then it turns out that this limit may or may not exist. It's called an indeterminate form of type 0 over 0. So what do I mean by indeterminate form? I mean that the limit cannot be predicted based on the given form. It may or may not exist. It could be 17, it could be negative 1/2. You have to do more work. You have to change the form so that the limit can be revealed. The answer can be revealed. So to illustrate that, take a look at these three examples here. In the first example, we have the limit as x approaches 1 of x minus 1 cubed divided by x minus 1. When I try to plug in 1, you can see that the bottom is approaching 0. And similarly, the top is also approaching 0. And so to evaluate this limit, I can actually just cancel one of the factors. I have 3 copies of x minus 1 on the top, cancel 1 copy on the bottom, and I'm left with 2 copies on the top, like this. And then you can use direct substitution to solve this limit. The answer is just going to be 0. So you can see that in this case, we had this sort of indeterminate form of 0 over 0, and the answer was simply 0. Now let's slightly modify this example. Let's consider the limit as x approaches 1. And I just sort of flipped the fraction here. I have x minus 1 on the top and x minus 1 cubed on the bottom. This time, when I cancel, I get x minus 1 squared on the bottom. And when you plug 1 in over here, then you're basically doing 1 divided by a very tiny number. And since it's being squared, it's always going to be positive. So this is going to go to infinity. So in this case, the limit did not exist, right? Infinity is not a number. This limit technically doesn't exist. But we write this just to show why it doesn't exist. Okay, and now let's take a look at the last example. Let c be your favorite real number. Then let's consider the limit as x approaches 1 of c times x minus 1 over x minus 1. These x minus 1 factors cancel, and we get the limit of this constant. And the limit of a constant is just the constant. And so this way, the limit just evaluates to any constant, right? You can pick 5, and the answer at the end would just be 5. And you can see in both cases, the numerator and denominator both approach 0. So what this is showing is that when the numerator and denominator are both approaching 0, then you cannot say anything about the final answer. And so this is what we call indeterminate forms. The limit cannot be predicted from the given form. You have to do more work. Now similarly, let's suppose that you're trying to evaluate a new limit, the limit as x approaches c of f of x over g of x, and this time you find that both the top and bottom, the numerator and denominator, are going to infinity, or maybe one's going to minus infinity and the other one is going to positive infinity. It doesn't really matter, but they're both becoming large in magnitude. Then this is another indeterminate form. This is called an indeterminate form of type infinity over infinity. And the notation that you see over here is just a symbol. It's used to represent the limiting behavior of the numerator and denominator. It's just a symbol that we're going to be using throughout these lessons to indicate what type of form we're working with. Now you can do the same exercise and construct examples that show that sometimes the limit exists, sometimes the limit doesn't exist. But for now, I'll just skip that. The idea is very similar to what I described above with the case 0 over 0. Okay, awesome. So now that we have learned about the indeterminate forms 0 over 0 and infinity over infinity, well, guess what? There's something called L'Hopital's rule, and this will help us evaluate these exact indeterminate types, 0 over 0 and infinity over infinity. Now, just before we take a look at the statement of the theorem, let me just mention one more thing here about something called determinate forms, okay? Something that's not indeterminate. So whenever you have 0 divided by any number like 17, something non-zero, well then it's always going to be 0. You can try it on your calculator, just try taking 0 and divide it by any non-zero number, okay? The result will always be 0. Similarly, if you see that the top is approaching 0, and then the bottom is becoming very large in magnitude, right? It's approaching plus minus infinity. Then this is again not indeterminate. It's actually determinate. The answer is just going to be 0. The 0 divided by a big number is still going to be 0. Next up, let's say you have a non-zero number here, maybe 17, and you're dividing by something very small. Then the result will be approaching plus or minus infinity, and it will depend on the sign of the number here, 17, And then it will also depend on how you're approaching 0. Are you approaching from the left-hand side? Or are you approaching the right-hand side? So the answer will definitely blow up to infinity, but to determine the sign, is it plus infinity or minus infinity, you have to do analysis based on the signs. Similarly, suppose that the numerator is approaching a very large number. It could be very large and positive or very large and negative, and you're dividing by something very small. If you try taking a very large number and dividing it by a very tiny number in your calculator, this will become even larger. It will become even larger. And so the result is going to approach infinity. Now, is it plus infinity or minus infinity? Again, you have to analyze the sign. If they're both positive numbers, then you're going to go to infinity. If they're both negative numbers, you're still going to approach infinity. But if the signs are opposite, like minus or plus or minus, then the result will end up to minus infinity. Okay, so just keep this in mind. These are not indeterminate forms. So whenever you see something like this, whenever you see a form like this, there's no need to do extra work. You can just put the answer right there on the paper. Now let's take a look at the statement of the theorem, L'Hopital's rule. So let's suppose that you're trying to evaluate a limit of this form. The limit as x approaches c of f of x divided by g of x. Okay, so you're working on this limit. Then here's what L'Hopital's rule says. Suppose that f and g are both differentiable and that the denominator is non-zero on some open interval that contains your limit point, c, right? Remember, c is the limit point. And here's the thing. It's okay if these conditions are violated at the limit point. And now let's suppose that you have one of these two cases. Both the numerator and denominator are approaching 0 as you approach your limit point, or both the numerator and denominator are becoming large in magnitude. So they're both approaching like plus infinity or minus infinity. It doesn't really matter. You can have any combination. So in other words, we basically have an indeterminate type of 0 over 0 or infinity over infinity as we discussed above. Then it turns out that to evaluate this limit, you can consider the limit of the quotient of derivatives. So it's really that simple. To evaluate this limit, we can consider a brand new limit where you just differentiate the top and you differentiate the bottom and you see if this limit exists. Okay, and this is also important. For L'Hopital's rule to apply, the limit on the right-hand side must exist, right? So this should be a real number or it should be plus minus infinity. Okay, so be very careful with that, because if at the end you get some oscillating function like sine x or cosine x where the limit doesn't exist, well then all bets are off. You cannot use L'Hopital's rule to conclude that the original limit doesn't exist or oscillates. Okay, so be very careful. You want to make sure that this answer is either a number or plus or minus infinity. Then you can conclude that the original limit that you're working with is also that number or plus minus infinity. Now, just before we jump into the examples, I want to mention two important points. When we're applying L'Hopital's rule, we're differentiating the numerator and denominator separately. Okay, so when you take a look at this statement here, notice that we're not applying quotient rule. Okay, we're not applying quotient rule. We are differentiating the top and bottom separately. Okay, so please keep that in mind. That's what you have to do. It's much simpler than applying quotient rule. And the other point I want to mention is that L'Hopital's rule can also be applied for one-side limits, like maybe you're approaching c from the left-hand side, or you're approaching c from the right-hand side. Or even if you're trying to do a limit at infinity, like the limit as you approach plus minus infinity. Then again, as long as the assumptions of L'Hopital's rule are satisfied, then you can apply it. Okay, so L'Hopital's rule is very, very powerful. It's going to help you evaluate tons of limits, right? Infinite limits, one-side limits, regular limits. Just make sure that the assumptions are satisfied before you apply it. Okay, so let's take a look at our first example. Let's evaluate the limit as x approaches 1 of sine of pi x divided by ln x. So the first thing you should do is try to plug in 1. Like, what happens as we approach 1? Well, as we approach 1, this is just going to be sine of pi. And sine of pi is going to approach 0. Okay, so the top is approaching 0. Similarly, ln of 1 is also 0. So this is also approaching 0. So we have 0 over 0. And then also, these functions are both differentiable, right? So we can apply L'Hopital's rule here. And what we have to do is differentiate the top and bottom separately. So the derivative of sine is just a cosine. You keep the inside the same. And then by the chain rule, you have to multiply by the derivative of the inside, which is just pi. That's how I got pi. And then the derivative of ln is just 1 over x. The other thing I would like to mention is that whenever you apply L'Hopital's rule, that is when you differentiate the top and bottom, it's helpful to write like a small h on the equal sign. It's definitely not needed, but it's helpful to write that to keep things organized. Now what we should do is try to plug 1 in again. Let's try to plug in 1. So if I try plugging in 1, the bottom is just 1. And cosine of pi, well, cosine of pi is just -1. So what we have here is actually a negative pi over 1 or negative pi. And that's the final answer. Okay, since this limit exists, the original limit is going to be equal to this limit. It's going to be negative pi. Okay, let's take a look at the next example. In this example, we're taking a look at the limit as x approaches 0 of sine of x minus x divided by x squared. So the first thing you should do is try to plug in 0, like see what's happening as we approach 0. Well, the bottom is definitely going to approach 0, and the top, sine of 0 is 0, and yeah, this is also 0. So yeah, the top and bottom are both approaching 0. That's what's indicated by this symbol over here. Also, the top and bottom are both differentiable, so we can go ahead and apply L'Hopital's rule. Now let's differentiate the top. Well, the derivative of sine is cosine, the derivative of x is just 1, and then the derivative of x squared is just 2x. Now try plugging in 0 again. See what's happening to the numerator and denominator. When you plug in 0, you can see that cosine will approach 1 when you plug in 0, and you have 1. So 1 minus 1 is 0. That means the top approaches 0. Similarly, when you plug in 0 on the bottom, 2 times 0 is 0. So again, we still have 0 over 0. We still have this indeterminate form. Well, guess what? We can just apply L'Hopital's rule again. You can sort of keep doing this. So let's go ahead and apply L'Hopital's rule again. Let's differentiate the top and bottom. On the top, we'll just get minus sine x. On the bottom, we'll just get 2. And now let's try plugging 0 in. When I plug in 0, sine of 0 is just 0. And then the bottom is just constant, so 2. Now 0 divided by 2, that is just 0. 0 divided by any non-zero number is just going to be 0. As we discussed before, it's a determinate form. Okay, now let's take a look at the next example. Here, we're trying to evaluate a limit at infinity. The limit as x approaches infinity of e to the x over x squared. So the first thing you should ask yourself is what's happening as you approach infinity. As you approach infinity, e to the x is going to blow up. This is also going to go to infinity. And x squared is also going to go to infinity. So we have indeterminate type, infinity over infinity. Also, both the numerator and denominator are differentiable. So L'Hopital rule applies. We can just differentiate both the top and bottom. The derivative of e to the x is just e to the x. The derivative of x squared is 2x. Now you should try plugging in again. In this case, as you approach infinity, e to the x will approach infinity, and this line down here, 2x, is also going to approach infinity. So we still are in indeterminate form. That's okay. Just go ahead and apply L'Hopital's rule once again. This time, the derivative of e to the x is just e to the x. The derivative of 2x is just 2. And now, when you take the limit as you approach infinity, you have e to the x approaching infinity divided by 2. Now, taking a very large number, dividing it by 2. So it's still going to be a very large number. This is not indeterminate. This is actually just infinity. Great, now let's take a look at this next example. So here we have the limit as x approaches 0 from the right-hand side, so a one-sided limit, of natural log of x divided by cotangent x. So when you plug in 0 from the right-hand side, remember, the graph of ln looks like this. So as you approach 0 from the right-hand side, ln is going to go to minus infinity. So that's what we written over here. And cotangent, you can just think of it as, for instance, cosine over sine. So when you plug in 0, cosine is going to approach, well, cosine of 0 is 1, and then sine is going to approach 0. And since we're approaching from the right-hand side, it's always going to be above 0. So it's 1 divided by a very tiny positive number. 1 divided by a very tiny positive number, it's going to blow up to infinity. Okay? And so that's how I sort of reason about how we got infinity here. So this is also an indeterminate form of type infinity over infinity. It doesn't really matter if they have different signs. It's still of the same type, infinity over infinity. And the numerator and denominator are differentiable. So L'Hopital's rules applies. The derivative of ln is just 1 over x. The derivative of cotangent, this one's a little bit rare, but it's negative cosecant squared x. And so now we want to try plugging 0 in. Again, if you try plugging 0 in, you're doing 1 divided by a very tiny positive number. So it's going to go to infinity. Similarly, cosecant is 1 over sine. So sine of 0 is going to be 0. So you're doing 1 divided by a very tiny number. It's also going to be infinity. Okay, in fact, it's be like minus infinity because of minus sign here. But it's still infinity over infinity type. So it's indeterminate. And we can apply L'Hopital's rule again. But before we do that, because things are now getting complicated, let's try to sort of simplify this a little bit. Let's try to rewrite this. So what I want to do is, since cosecant is just 1 over sine squared, we can just move it up. We can just move it up and we'll get the sine squared on the top. And then this x we can just move down. Now this is a little bit simpler to look at, and as you approach 0, then the bottom approaches 0 and the top approaches 0. So we changed the indeterminate form to type 0 over 0, but L'Hopital rule still applies. So when we apply L'Hopital's rule this time, to differentiate the top, you have to use power rule with chain rule. So we get, you bring the exponent down, you keep the inside function the same, and then you multiply by the derivative of the inside function, which is cosine x. That's the derivative of the numerator. The derivative of the denominator is just -1. And so now when you try plugging in 0, you'll see that sine of 0 is just 0. So this part will just go to 0. And then that makes the entire product go to 0. So we have 0 divided by -1, and this is not indeterminate. The answer is just going to be 0. The 0 divided by any non-zero number is 0. Great, now I have two very quick examples just to show you that you want to be careful when applying L'Hopital's rule. So let's take a look at this limit here. The limit as x approaches 1 of x squared plus 5 divided by 3x plus 4. So if you try to blindly apply L'Hopital's rule, just differentiate the top and bottom, then you'll end up getting the wrong answer. And the reason for that is you always have to check how the numerator and denominator are approaching and make sure it's of the form 0 over 0 or infinity over infinity. Well, when you plug 1 in here, you get 1 plus 5, which is 6. And when you plug in 1 down here, you get 3 plus 4, which is 7. So this is actually not indeterminate. You can just solve this limit by direct substitution. It's a continuous function, and this limit point is in the domain of this function. So by direct substitution, you get the answer, 6 over 7. If someone tried to just blindly apply L'Hopital's rule, we have the work on the side here. You would differentiate the top, you would get 2x. You differentiate the bottom, you would get 3. They would plug in 1 and get 2/3. Okay? And so they wouldn't realize they made a mistake, but it's actually the wrong answer. Okay, so before you apply, please always make sure that it's in the correct form, 0 over 0 or infinity over infinity. And here's another example. The limit as x approaches 0 of sine of 4x divided by x squared plus 3x plus 1. So when I plug in 0, you'll see that sine of 0 is just 0. And when you plug in 0 on the bottom, you just get 1. So the top approaches 0, the bottom approaches 1. That's what this symbolizes. And so this is not indeterminate. In fact, 0 divided by any non-zero number is just going to be 0. So the answer to this limit is just 0. L'Hopital rule doesn't apply here. Great, so that brings us to the end of this video, in which we introduced the indeterminate forms 0 over 0 and infinity over infinity. And we introduced L'Hopital's rule that helps us tackle these types of indeterminate forms. Now in the next few videos, we're going to take a look at some other indeterminate forms, because it turns out that the L'Hopital rule can also be used to evaluate limits involving other indeterminate forms, like indeterminate products, like 0 times infinity, indeterminate differences, like infinity minus infinity, and also indeterminate powers, like 1 to the infinity, infinity to the 0, and 0 to the 0. It turns out all of these forms are also indeterminate. Okay, so we'll take a look at each of these in detail. And I have a note over here for those that are curious. You might be wondering how come something like this is indeterminate, but something like infinity over infinity is not. And so, yeah, we'll talk about that in detail as well. We'll see why these are indeterminate and these are not. These are actually determinate powers. Okay, so stay tuned for that, and I'll see you then. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.